Well, I'd like to thank the organizer for giving me the possibility of presenting this work that I carried out in collaboration with George Revelli. Well, why are the borders of Palestine, Israel, and Wallonia, Flanders so different? This is an entropic analysis of a Schelling model with hierarchically structured initial condition. As you can see, the border separating Wallonia and Flanders in Belgium is by far more regular than the border between Israel and Palestine. A regular border between two nations and or culturally different groups of people is something that contributes to the existence of territorial conflicts. This idea has already been studied. For instance, you can glance the works by Janet Barjam. I am mentioning over there. In connection with this series problem, we studied the Schelling segregation model for minorities. As you know, simple models analyzed under a more proper perspective can sometimes provide interesting visions. The arrangement of pixels on the right basically represent two segregated groups of agents. The minority, which is conformed by the yellow pixels, constituting something between 5% and 40% of the total. The majority conformed by the blue pixels, and the red pixels are empty sites that a priori have no owner. They constitute 1% of the total, which models the lack of resources or land. The system evolves according to the Schelling's upper rule. If an agent is surrounded by more individuals belonging to the opposite social group, he will move to some randomly chosen empty place in which he becomes surrounded by comparatively more individuals of his own social group. As time goes by, the system will converge to a final and stable configuration of pixels. Well, at least it is widely known that this happens for random initial conditions. However, in this work, we explore hierarchically structured initial conditions. Actually, we assume that the pixels of the minority conform a pattern that has fractal dimension D, which ranges between 0 and 2 and is computed with the box counting algorithm. Let us point out the difference between random and structured initial conditions in terms of the average convergence time. In order to avoid infinities, the convergence time is normalized according to the formula shown on the right. 0 means zero convergence time and 1 means infinite convergence time. For random initial condition, we can see that the convergence time is on average infinite, except when the minority represents more than approximately 40%, something that does not properly correspond with the idea of a minority. In contrast, for hierarchically structured initial conditions, the convergence time has a minimum when the minority is more or less 20%. Infinite convergence time can also be reached, but they basically occur outside of the model, when the minority tends to be either negligible or more than 40%. Let us describe the convergence time in terms of the fractal dimension of the minority. As we can see, there surprisingly exists a quasi-functional relationship between the convergence time and the fractal dimension, independently of the size of the minority, which ranges between 0% and 40%, as I mentioned before. You can see a minimum. It may have to do with an article about general complex system becoming out of control that I published in 2015, and George Revelli mentioned yesterday. That article defines an entropy function computed by taking the logarithm of the total number of pattern configuration of pixels having fractal dimension D. The range given by approximately D1 equal to 1.77 and D2 equal to 1.51 can be defined by the entropy function and was pointed out as the most uncontrollable regime. We claim here for the Schelling's model that the range D2, D1 correspond to a regime in which the system behaves in the most segregationist way. Let us put the latter in terms of entropy absolute variations. On the one hand, for D lower than D2, the lower fractal dimension of the minority, the lower variation of entropy, which implies a lower system evolution. This case corresponds to small minority groups conformed by almost scattered agents that may represent no competence for the majority. On the other hand, for D greater than D1, the same happens as D increases. There is no substantial evolution. Agents basically stay there and tolerance prevails. Note that the minority tends to be more compact and having more properly demarcated borders. The highest variation of entropy occurs when D approximately lies on D2, D1. We can see how the initial and final configuration look very different at a glance. It naturally implies evolution. The system behaves in the most segregationist way because many agents have to move. In other words, there is low tolerance. In that plot, in the former plot, it was actually computed the entropy of the borders of the minority patterns. The reason is that for hierarchically structured initial conditions, the fractal dimension is basically time invariant. In this figure, you see how D at t equal to 0 is basically equal to D at t equal to infinity. This means that the system evolution basically occurs at the borders of the patterns. Well, let us focus on the borders. On the figure, I show the distribution of the fractal dimension at t equal to 0 and t equal to infinity. They are always lower than D1 because of a geometric property that I could explain later. There is no bias in the generation of the initial configurations. Note that, first, the borders are basically volatile patterns under a Schelling update rule because they mostly lie on the most uncontrollable regime. Second, the borders move toward another regime, namely D3, D2, that is also defined in terms of the entropy function. Actually, the different dynamics can be characterized in terms of entropic regime variations. Let us break into part the later histograms according to the dimension of the minority. For D lower than D2, the borders stay at the same entropic regime. They do not substantially change their shapes. For D greater than D1, the borders stay at the same entropic regime. There are well-defined borders and there are non-substantial shape changes. However, for D lying in the most uncontrollable regime, there is a clear entropic regime variation. The same analysis can be performed for the unsatisfied agent. An agent is unsatisfied when he is surrounded by more individuals belonging to the opposite social group. The unsatisfied agents are part of the borders. Their dimension cannot exceed the 2 because of other geometrical reasons that can't be explained here. However, I'd like to mention that the unsatisfied agent can be characterized as the most dynamic part of the borders. Actually, they undergo a wider entropic regime change, which is enhanced when the minority lies at the most segregationist regime. The conclusion, well, they are the ones of the article I am showing here, which is currently online. It has been published today. By adding hierarchically structured initial condition to the most basic Schelling model, the time evolution is quite different. in comparison with assuming random initial conditions, which are usually found in the literature. Many social filters are naturally reproduced without introducing artificial parameters into the model. Secondly, D is time invariant, that is, dynamics occurs at the border of the majority patterns. In other words, system macro structure does not change. It corresponds with the idea of a kind of local idiosyncrasy that mostly determines the system particular fate. Actually, for D outside of D2D1, tolerance and status quo prevail. Time just passes by with a relatively non-substantial system evolution. When D lies inside of D2D1, segregation easily blows up. Moreover, in the paper we describe how these recurrent segregation processes are more likely to occur there. However, one should include into the model some regeneration mechanism, perhaps percolation. In addition, D2D1 is the most segregationist regime and basically coincides with one I pointed out in my 2015 article in a far more general context. Well, thank you for your attention.